Using the milling machine, we can actually cut circular cams. If you have a look at this picture here, you will notice that the dividing head is set on the table and it is geared to the lead screw. Now we know dividing heads will make 40 revolutions of the worm shaft in order to make one complete revolution of the chuck. So using this principle, if we gear it to the lead screw of the milling machine table, if the lead screw makes one revolution, then the dividing head should make 1/40th of a revolution at the chuck, assuming it is geared 1-to-1 in the backside. This particular milling machine has a screw of 5 threads per inch, or each revolution of the screw is 200 thou. So assuming 40 turns of the worm shaft in the back of the dividing head will cause the chuck to make one revolution, the lead of the table, or the amount of distance the table will travel on the milling machine, should be 200 thou times 40, or 8 inches. Looking at the milling machine from the end, you can see the change gears. The gear on the bottom is coming off of the lead screw just underneath the table of the milling machine. It's meshing with an idler, which is then meshing with the gear going into the worm shaft of the dividing head. You can see the back of the dividing head just above it. Again, if the gear off of the lead screw and the gear going into the worm shaft had the same number of teeth, it would be a 1-to-1 ratio. In other words, the table would move 8 inches for every revolution of the chuck, or 40 turns of the lead screw on the very bottom gear. Often not too much of a lead, so we need something that's a little more manageable. In this case here, you will notice that there are twice the number of teeth on the lead screw, or the gear on the bottom, as compared to the gear going into the worm shaft on the top. So in other words, the gear on top will make 2 revolutions for every turn of the gear on the bottom. So we can take that 8-inch table lead and we can make it more manageable. In other words, the table will now move 4 inches for every revolution of the chuck. Okay, because we got 2-to-1 gearing in the back of the dividing head from the lead screw, the table will move towards the dividing head 4 inches for every revolution of the spindle of the chuck. If the part being held in the chuck was straight up and down and the end mill was to touch the side of this part, what would happen is, as it made one complete revolution, the end mill would be 4 inches closer to the center of the part. Sometimes that is not the lead we want of the cam, so we can actually tilt the dividing head on an angle to get the lead we want. So if you can see here, what we've done is we've created a triangle. This side becomes the lead of the table, or the 4 inches. This side becomes the lead of the cam, or the 2 inches. If we set this angle here, or calculate what this angle is, and this is just a sine function, opposite over hypotenuse, and we can set the dividing head to this angle from horizontal. In this case here, because we need a 2-inch lead of cam, the dividing head will need to be set 30 degrees from horizontal. This angle here is the angle of the spindle from vertical. So 30 from 90 will leave 60 degrees, so that spindle will be tilted 60 degrees from vertical, and then we can start to cut the cam. The end mill needs to be at right angles to the face of the cam, or the outside diameter of the cam being cut will not be parallel to the axes of the cam. We're going to turn on the spindle, and now we're going to turn on the feet of the table, and the dividing head will start to turn. And what will happen is this end mill will now start to cut into the part at a rate of 2 inches per revolution of this chuck. After the first lobe is cut, one of the change gears is taken off the back of the dividing head so that the dividing head will not move and the table is moved back to the original position. In this case, it's ½ inch for each lobe. Here's a picture from the back of the dividing head with the gear being pulled off, so the dividing head will not turn when the table's being moved. If you have a look at the end mill, you can see the table is being moved away from the cam itself back to its original position. In this case, the rise of the cam, which is ½ inch. You can see the end mill starting to come away from the cam. There's a dial indicator on the table. The operator's watching the dial indicator to get the rise of the cam. This picture zoomed out a little bit so you can see exactly what's happening with the feet on the table and the dividing head turning. And we're going to work around the outside diameter of this blank until we get all of the cam lobes cut. In this case, it will be 4. And here's a close-up of that final lobe being cut. So this will be a 4-lobe cam. Its rise will be ½ inch, and the lead of the cam, or the distance, if we were to go around one complete revolution, will be 2 inches, which is why the dividing head was set at an angle for that 4-inch leaded table. Looking down at the table, this is a dial indicator that is measuring the movement of the table. Again, the table has a 4-inch lead. Because it's a 4-lobe cam, we'll want this dial indicator to move 1 inch for each lobe of the cam. And here's the finished product. This is the rise of the cam. In this case it's 1/2 inch. Because it is 4-lobe cam, if we were to follow the arc around one complete revolution, it would be 4 times the rise of the cam, which is the lead of the cam. In this case it would be 2 inches. So we'd set that dividing head at an angle so we can get a 2-inch lead of cam.